Yeah, so welcome back. So yeah, these are my given parameters for the design of retaining wall. Our small h here means the height from the ground floor, the usable ground level, to the retaining wall height, like the peak of the retaining wall. And here the gamma soil is the density of the soil, and this angle here is our frictional angle, and this is the frictional coefficient, the coefficient of friction. And our PA is the bearing pressure of the soil, which is 160 kilonewton per meter square. And our FCU is the concrete strength, the compressive concrete strength, of course. The FY is the tensile strength of the reinforcement that we are using, the yield strength. And then gamma concrete is the self weight, like the unit weight of the concrete, which is 24 kilonewton per meters cube. And that's what is called not necessarily density, but that's density. Then firstly we have to get our Ka, which is the coefficient for the active pressure. The active pressure is the pressure that is acting due to the retaining soil, due to the retained or retaining soil, which is this side. And the passive pressure comes from the from the little backfill of our toe here. So that's what the passive pressure is. Then our Ka, this Ka here just stands for a coefficient of this pressure. So this, the formula is 1 minus sine of this theta here all over 1 plus sine of theta equals is equal to 0.33. Then here to same thing, just the inverse, just the inverse of this, we get our Kp, which is the passive coefficient. Then our df here is the height from the ground level to the very bottom of the foundation of the footing slab, base slab. So that's what it is, and this is the formula P. Remember, our P is this, which is 160 kilonewton per meter square over the gamma of soil, all multiplied by I believe, yes, active coefficients square. So here we are getting 0.8, say 0.9 meter. So we can continue. So getting df to be 0.9 meters, we can say we can add h, which is, as I said, from this ground level, usable ground level, to the peak of the retaining soil, the retaining wall, is h. Now to now get the total height of the retaining wall, we say small h plus df would give us 8.889. So here we can assume, since our pressure is not so, no, this does not have anything to do with pressure, because of our steel yield strengths, we are using, what was it here? So we are using a mild steel to design. So let's consider the depth of 300 mm for the stem at the top. So the distance or the thickness of this stem is 300 mm. Normally it should have been 200, but I chose 300 because of our, again, yield strength to be we are using a mild steel, as I mentioned earlier. So we are assuming this to be 300, and the depth of our B, which is the, no, sorry, not the depth, the width of our of our base, of our slab base, the foundation base, is gotten by the from the formula between, actually between, should have been between 0.4 to 0.6 h. The h again is the total height from here to here. So that's it. We can just choose any value. Yeah, I chose to use 0.5625 multiplied by the h to give us a singular whole value, which we have here as 5 meters. Then our TP, what is our TP? Where is the TP? TP is the let me see. So TP is the toe projection, which is from just from the face of this bottom stem up to the edge of the toe. That's our TP, toe projection. And it is gotten by the formula B. The B we got here over 3. And we have that to be 1.667 meters. But then because of our bearing pressure not being so high, because when we don't have enough area to spread the load on top of our soil, it tends to fail in pressure. It overburdens our soil, so it fails in pressure, like the pressure that it's exerting on the soil will be too much. So we need a larger area to spread our footing on. So yeah, I've changed this. I've redefined this to be 2.5 instead of this 1.66. So our toe projection is now 2.5 meters. Then our B again, because if this one changes, then definitely the total breadth is going to change, of course. So I've now changed the breadth to be 6 meters, not considering what we have from the formula again. What this entails is that it is not saying this breadth this width should not be more than this. It's just giving you a just it's like a thumb rule to easily get your dimensions. There's no rule or code that says it shouldn't be more than 0.6 h. So that's that. Now we go to the base slab. So the thickness of the base slab would be h over 12. This here translates that the depth, the thickness of the base must not be less than 740.7. So you can use anything higher, which I chose to use 0.75 meters, which is 750 mm. That's our, you see, that day is our wait, I'm going to change this because I've redrawn this somewhere else, so give me a moment. So let's just continue with this. So this is what I'm saying. So this side, where is it? So our depth here is 0.7, yes, 0.75. So let's just continue. Oh, as I said earlier, this 0.3 is the stem at the top stem, and then this here is what we have as question mark here. We are going to see where we imputed it subsequently. So that's that. Then again, the toe projection is this, which we chose as 2.5. Then the total the total width is now 6. This should have been 6. So that's 6. Then the height, the h from here to here is 8. Then the total h is 8 points. No, not the total h actually. We will get to what we are talking about later. Okay, yeah, this is it. So yeah, these are the elements we are designing for in this retaining wall. We are designing for a stem wall, which is the stem is this, and the heel slab, this is it. Then the toe slab, this is the toe slab. And then this shaky only applies when your passive force is higher than the resisting force coming from the passive side. So it tends to like shift this towards this side. So to now resist that, we need shaky. Though the friction of the soil itself can resist it, but if the friction is not enough, we introduce shaky. that would like project from just maybe below this, or might be even towards this side. So firstly, we are trying to design the stem wall. So the now before we can actually get the stem wall thickness or the design at all, we need to attain this height. This height from here to this place, we need to attain the height. This is how we attain it. The small h, which is this, plus df, minus then minus the tb that we got, which is this. The tb that I said is the thickness of the base slab. No, this is the total h, the big h, minus this. That's basically what we have here. Then this is what it gives us, which is this that I said we are going to reach later. So that's that. The next one is now getting the moments. We are trying to get the moment of the moment induced on this wall due to the due to the active pressure of the soil. This, come on, let me bring a pen. There are soil everywhere here. In a few. Okay. So this soil here. Okay, yeah, this soil here would want to, push this like this, acting like this. This is the active pressure from the retained soil. Would want to push this like this. Then later you would understand that this would want to go like this due to the pressure acting like this, or due to this one trying to move like this. Then this one will be acting towards the side. This is basically how it's going to be. Then the head pressure would push this one here, because this coming like this, the pressure coming like this would want to exert pressure on the soil, and the soil would react back, making this fail this way. This is how we design retaining wall, especially for especially retaining wall that is retaining soil, just like we have here. So that. So now we are here. We are here. So the design, no, sorry, just the maximum moment is this. This is the formula. Ka, the active coefficient multiplied by the soil pressure. Sorry, the soil unit weight, which is what we had to be 20 kilonewton per meters cube. Then the height. This is the height. The this h, where is it? Yes, this active soil height, which is again, as I said, this retained wall area or retained soil area from here to here, cube over 6. Again, the active coefficients, the soil density, the height of the soil, cube over 6. We get almost 600 kilonewton meter. Then, as retaining material, we can take it out, like it can be replaced with another material, or even left opened on like unloaded, or that's why it is kind of classified as life load. And in bs code in bs code we have our magnification factor to be 1.6 for life loads, which is why we are multiplying it by this 1.6 factor, magnification factor, to make it 958 kilonewton meters. So now this is our design or ultimate moment for the retaining wall. Now recall, this is the formula for getting this same ultimate moment. Now we are going to equate this with this moment that we got here, just to find our D, the adequate depth for the bottom stem, the adequate thickness of this, since this is what we are designing for, and this is the most critical position of the stem, the bottom, because that's a fixed point. This is the free end. This is just like a cantilever, so getting, like, trying to find D, we are going to equate it, which is, M ultimate is equal to this, just to remember, just to, like, recall. Then making D subject of the formula from here, making this subject of the formula, we have square root of, you should understand this, so let me just skip it. Now we've gotten our D. The minimum D you can get, you should use is 418.977 mm. Yeah, I'm taking D to be 450, and the total thickness, considering the cover and the seal bar, so we are taking our D to be 450. As I said again, it's not compulsory you use this exactly. This just means it must not be less than what we have here. That's the minimum depth you can have. Again, since we have our top stem to be 0.3, now we've now determined or gotten our bottom stem to be 0.45. I mean, that's the D, and the thickness is still 500. So now we can proceed to the design, to the structure, to the design for the reinforcements. Now, since we've gotten our D to this, now we are now checking if, after providing the D to be this, if the ultimate moment is going to be higher than the design moment. We've checked it, and it is indeed higher than it. This is 1105 kilonewton meters, while the design moment is just about nearly 1000, which this is higher than it. So we can proceed. So since MU is greater than M, just design your reinforcements K equal to, as you know, MU over FCU times our B. Our B is 1 meter strip, then our D, then getting your Z to be this. And remember, your Z must not exceed 0.9. This is just a check, so you've checked this to be less than 0.9, so you can proceed to multiply your Z by the depth, which is, we got this, and to our area of steel, and we have 12,003 mm square. So checking our area table, we've gotten the provided area of steel to be Y40 at 100. So that's at 100. You might be seeing this to be weird. It is because of the fact that we are using mild steel. That is literally why it is that high. I mean, the area of steel required, and we've sufficiently provided something that is a little bit higher than it, so we are good. And 100 mm spacing is not so bad, so just leave it. We still have about 80 mm for the compaction of this thing, so it's still good. Now, since we've gotten this is our main longitudinal bars, then now we are now going to curtail, not to, as I said, this is the most critical area, the bottom stem, which this, like, as high as you go, as you go higher, the stress on the stem tend to reduce. So we don't need any reinforcement. We shouldn't need, but to conform with the code, we have to provide minimum at where we don't really require much steel. But then where we have to curtail it is at the point where we have the half of what we got as the bending moment, which is this. This is the design moment. Half of it, we are going to have this and know the position where it lies along the stem, which is, so getting the half of our moments. What is the half of our moments? Just the the ultimate moment divided by 2. That's the half. That's half of it. We've halved this moment to be this. Then we are going to equate it and look for and check for the new heights, the half, the halved heights. So changing, making each half subject of the formula. So we have this. You should understand how we, make it the subject of the formula. This multiplied by this, then dividing all through by Ka gamma soil. So that gives us 7.5 meters. Ignore this because this still equal to 1. So we've round it up to 7.6 to have a balanced or something that makes sense to be able to compute. So we have the heights at which our moment is halved to be 7.6. Now what that means or entails is that, oh okay, we are going to get there subsequently. Let's get there. So we are going to quickly design the or check, I mean, the average area of steel that we need. Now we are going to take the average of, as I said earlier, the depth or the thickness of this stem at the bottom is higher than the stem at the top. So we are going to take average of it. Remember, our stem at the bottom is 500 mm, then the top, sorry, the top is 300 mm and the bottom is 500 mm. We are going to add them and divide by 2. We have 400. 300 plus 500 is 800. Divided by 2, you have 400, which is the average of the bottom and bottom width or thickness of the stem slab. So from BS code, we are required to provide 0.24% of the cross-sectional area, which is B times the thickness, that's the area of the slab. And our B is 1 meter again, as usual, because we are designing for a meter strip or a meter width of slab. Then this is the secondary or minimum. AS minimum is now determined or gotten to be 960 mm square. We are providing Y16 at 200, which is just enough to resist this action, or just to conform with the code. This is not resisting anything, just to distribute the load efficiently along the span of the retaining wall of the SEM. So that area gives us 1010 mm square. So what we just calculated there, this height, what it means is, I would need to draw some things. So what it means is that, from this place, again, from this place to this place is, I think, yes, we have it here, 8.14. But then that 7.6, yes, that we actually got means that at a point here, at a point around there, the bending moment that is caused by the the retained soil is halved at this point, at which the height is 7.6. So what we are going to do is that we are going to provide just half of what we've been providing along the span on this to this place, to this point. So this other one would be the spacing will be halved, which means this will be at 200. You see, at 200, instead of 100, it is R40 at 200 instead of it to be 100. So that's what it is. But then this longitudinal one here that still that extends up also is 200, meaning when you have two two bars side by side, meaning that that distance between here and here is still 100, still stands as 100, 100, 100, while the distance of this is 200. I don't know if this makes sense. I believe it should. So now we are now going to the stability analysis. This is where things start getting interesting. So we can do that one next time. So watch out for the next video.